Let's talk about a wild weather event you probably never see coming: sudden stratospheric warming, or SSW. It's one of those rare atmospheric surprises that can flip our weather upside down, often with little warning. To understand SSW, we need to head up to the stratosphere, a calm, frigid layer that sits about 10 to 50 kilometers above our heads. It's a place most of us never see, but it plays a crucial role in shaping our weather. Most of the time, the stratosphere is icy cold, especially over the poles during the long, dark winter months. Temperatures can plunge to extremes that are hard to imagine from the ground. But every so often, something extraordinary happens. The temperature in the stratosphere can suddenly skyrocket by as much as 50 degrees Celsius in just a few days, a dramatic and rapid change that's almost unheard of elsewhere in the atmosphere. That's what scientists call an SSW, a sudden, intense warming high above the North Pole. It's like a heat wave in a place that's usually frozen solid. It might seem distant and disconnected, but what happens up there can shake up weather patterns down here on the ground. SSWs can disrupt the usual flow of the jet stream, leading to unexpected weather far from the poles. Think of the atmosphere as a layered cake. We live in the troposphere, the lowest layer, while the stratosphere sits quietly above. Each layer has its own job, but they're more connected than you might think. Usually these layers stay separate, but when an SSW strikes, it blurs the boundaries, sending shock waves through the entire atmospheric system. The effects can ripple down, changing weather patterns across continents. So, what causes this sudden warming? Giant planetary waves, huge pulses of energy created as air flows over mountains or between land and ocean, slam into the stratosphere, compressing and heating it rapidly. It's like giving the upper atmosphere a powerful jolt. SSWs aren't about global warming. They're natural, recurring events that have been happening for decades, if not centuries. They're part of Earth's complex climate system, but their effects can be huge. A single SSW can trigger bone-chilling cold, heavy snow, and even prolonged winter weather far from the Arctic. Cities that rarely see snow can suddenly find themselves in the grip of a deep freeze. It's a perfect example of how a disturbance in one part of Earth's system can have surprising and far-reaching consequences elsewhere. The atmosphere is a global network, and SSWs show just how interconnected it all is. So, next time you're bundling up for a deep freeze or watching snow pile up outside your window, remember, the story might have started miles above your head in a place you'll never visit. SSWs are science in action, on a planetary scale. They remind us that the forces shaping our weather are vast, powerful, and sometimes completely invisible. They're rare, powerful, and a reminder that everything in our atmosphere is connected, from the highest clouds to the ground beneath our feet. And that's why meteorologists and scientists pay close attention to what's happening high above the clouds, because sometimes the biggest weather stories start where we least expect them. You've heard of the polar vortex. It sounds like a sci-fi villain, something out of a blockbuster movie, swirling ominously above the Earth. But the polar vortex isn't fiction. It's a real and powerful part of our planet's climate system, shaping the weather we experience every winter. During the long, dark winter months, the polar regions are plunged into near-total darkness, receiving almost no sunlight at all. This lack of sunlight causes the stratosphere to become brutally cold, far colder than most people realize. As the air chills, it sinks and begins to spin, creating a swirling band of incredibly strong winds that circle the pole. This is the polar vortex in action. Imagine it as a giant, invisible fence, keeping the coldest, densest air locked up tight over the Arctic, away from the rest of the world. When the vortex is strong and stable, that cold air stays put, and winters in places like North America, Europe, and Asia are often milder and more predictable. The winds that make up the vortex, known as the polar night jet stream, can reach speeds of over 100 miles per hour, forming a powerful high-altitude barrier that separates frigid polar air from the warmer air to the south. This separation is crucial for maintaining stable winter weather patterns, preventing sudden cold snaps in more temperate regions. But if the vortex weakens, wobbles, or becomes unstable, that fence can break down, allowing the cold air to spill out. That's when things get interesting, and much, much colder for millions of people. Sometimes the vortex can even split into several pieces, letting huge masses of Arctic air escape southward, triggering extreme cold snaps and winter storms. And what's the main disruptor of this system? It's called sudden stratospheric warming, or SSW, a dramatic event where temperatures in the stratosphere can rise by 50 degrees Fahrenheit in just a few days. An SSW can kick down the polar fence, unleashing frigid Arctic air across the globe and causing chaos in weather patterns far from the pole. That's why understanding the polar vortex is so important. It's the key to predicting and preparing for the wild swings in winter weather that SSWs can bring. The polar vortex isn't just a headline or a buzzword. It's the engine behind some of our wildest, most unpredictable winter weather events. So, the next time you hear about the polar vortex stumbling, remember, it means winter is about to get a whole lot more unpredictable. Picture the polar vortex as a massive spinning top of frigid air swirling high above the Arctic. This powerful circulation acts like a barrier, keeping the harshest Arctic chill locked away at the top of the world, far from most of us. It's this invisible force that helps maintain the icy grip of the polar regions, keeping the cold contained and the rest of the planet relatively milder. But then, a sudden stratospheric warming event, an SSW, strikes. Warm air surges up into the stratosphere, injecting unexpected heat and shaking up the system. The vortex's strong winds, which usually race around the pole, begin to slow down dramatically and sometimes even reverse their direction. The once tight, well-defined circle of cold air starts to wobble, stretch, and can even split into separate swirling pieces. Instead of a neat, stable circle, the vortex becomes an unstable oval or breaks into smaller, wandering fragments. These fragments of cold air are no longer anchored in the Arctic. They can drift southward, spilling into North America, Europe, and Asia. The SSW doesn't just open the gate, it knocks down the entire fence, unleashing a flood of Arctic air that can sweep across continents. This dramatic process begins high in the stratosphere, miles above our heads, and can take days or even weeks to work its way down to the surface. Meteorologists and scientists watch these changes closely, knowing that a major disruption above signals big, sometimes dangerous, changes below. The weakened or split vortex is a warning sign. A deep freeze, blizzards, or even record-breaking cold could be on the way for millions. It's a dramatic chain reaction, starting miles above the Earth and ending with icy blasts, snowstorms, and extreme winter weather at ground level. When the vortex stumbles, winter weather can turn extreme, fast, catching cities and communities off guard. That's why SSWs are such a big deal for forecasters. They can mean the difference between a typical winter and a season of wild, unpredictable cold. So, how does chaos in the stratosphere end up freezing your street? It's a domino effect. First, the polar vortex weakens, then the jet stream in the lower atmosphere starts to wobble. Normally, the jet stream flows west to east, keeping cold air north and warm air south. But after an SSW, the jet stream buckles, forming deep waves. These waves let Arctic air plunge south, while warmer air surges north. That's how a lobe of the polar vortex can bring record cold to the US, Europe, or Asia. Sometimes the pattern locks in place, keeping the cold around for weeks. An event 30 kilometers above the pole can close schools and freeze pipes thousands of miles away. It's a stunning example of how connected our atmosphere really is. Let's see this in action, the Beast from the East in 2018. In late February, a massive SSW triggered a deep freeze across Europe. The polar vortex wobbled, the jet stream flipped, and icy Siberian air blasted west. Rome saw rare snow, Amsterdam's canals froze, and the UK faced its coldest spell in years. Temperatures plunged, snow piled up, and travel chaos followed. This wasn't a random cold snap, it was a textbook SSW event. The pattern locked in for over a week, reinforcing the cold. It was a dramatic reminder. What happens high above can freeze cities far below. The Beast from the East was no monster. It was atmospheric science in action. And it all started with a sudden warming, miles above the Arctic. North America's turn. The Texas deep freeze of February 2021. A powerful SSW in January split the polar vortex, sending a lobe of Arctic air over North America. By mid-February, the jet stream dipped deep, funneling frigid air all the way to Texas. Dallas saw temperatures below 0 Fahrenheit, colder than parts of Alaska. The cold lingered, power grids failed, and millions were left in the dark. This disaster started weeks earlier with a stratospheric shakeup. When the polar vortex breaks down, its icy reach can extend thousands of miles. What happens at the pole doesn't stay at the pole. What causes an SSW? Giant atmospheric waves, called planetary or Rossby waves. They're created by air flowing over mountains and the clash between cold continents and warm oceans. Usually, these waves ripple around the globe in the lower atmosphere. But in winter, they can travel upward, carrying energy into the stratosphere. When they hit the polar vortex, they break, like ocean waves on a beach, releasing energy and rapidly warming the air. This slows or reverses the vortex's winds, triggering the SSW. It's not about the sun, it's an internal atmospheric dance, linking mountains, oceans, and the highest reaches of the sky. The strength and path of these waves decide how intense the SSW and the resulting cold will be. SSWs are big, so scientists work hard to predict them. Unlike pop-up storms, SSWs develop over weeks, giving forecasters time to spot warning signs. Supercomputer models track planetary waves and simulate the whole atmosphere. When a strong wave heads for the pole, it's a red flag. Models can often predict an SSW 1 to 2 weeks in advance, a crucial heads-up for extreme winter weather. Satellites and weather balloons feed data into these models, even from remote Arctic regions. Thanks to this science, we get early warnings when winter might take a wild turn. Why study SSWs? Because they're one of our best tools for long-range winter forecasting. A 2-week warning about a major cold outbreak helps governments, energy companies, and the public prepare. As the climate changes, understanding SSWs is even more important. Melting sea ice and warming oceans could make these events more frequent or intense. Each SSW is a natural experiment, teaching us about the planet's complex systems. From the beast from the east to the Texas freeze, SSWs show how the stratosphere and surface are linked. By studying the sky above, we learn how to live better on the ground below. So next time you hear polar vortex, remember, it's a story of waves, wobbles, and a spectacular warming that can bring the Arctic to your doorstep. Science connects us all, even to the coldest corners of our world.